So, hello. So let's go to the ExploreML one. There should be an email. Oh wait, you know what? Let's follow the guys in the email you got. Okay, I don't have it. All right. Hi everyone. Do you have the notebook set up? This notebook, the check IT setup.
Yes, I have it.
Okay, cool, great. Okay. I'm sorry. Then probably let's wait for a couple minutes so that all of us have the access to check IT and the notebook.
So I have a question about the collab.
Yes.
So, uh, the end, the ending of the file is pi notebook. Is it the
Right.
same as Python?
No, it's different. I was the IPy notebook is more of like combination between like Python IDE and the terminal.
Mm.
Yeah, so like most of the time when you code on a Jupyter notebook, um, it's hard. Most of the time it's only for development, you know,
Mm.
for the machine projects. But when you need to deploy it in production, you should move to DocPy files.
Oh, I see.
Yeah. All right. Let's start it. Yeah. So you guys can just continue in setting up the um, notebook and track IT because probably some of you still not have them set up. But let's go with this last. Okay. Yeah. Welcome to the second day of the experiment workshop. So today is second day of a series, and why we okay. So today is the second day of a series, and well, first let's ask the question: what is AI or artificial intelligence? Um, you probably heard of many times about Alexa, um, Siri, or like Tesla cars. So all of them, they actually AI technique. However, so I would say that AI is like a is software that make the machines to perform the human intelligent task. So some examples are that, let's say, think of a Google Translate on your phone, and then when you travel to like Russia, you can easily use a Google Translate to um, ask it to translate from your voice into Russian voice. So that's it's easier for you to communicate and travel. Um, Another like very medical apply application is ChexNet. So ChexNet is software developed by Stanford University. So this software used to used to detect and classify 14 diseases within the chest radiographs, and its performance pretty good, is equivalent to the Merck experts. So here I have the grayscale and the grayscale radiographs here. So these grayscales radiographs will be input into the ChexNet, and what the output are the color radiographs here. And for every mark or area that have the orange and yellow color, so these marks mean that those are the potential location of the diseases that the ChexNet detect. And based on intense the intense I would say the intensity of the color, the brighter it is, the more disease the worse the disease is. So underneath AI, we also have machine deep learning. The reason why we have two subfields because AI is a very broad term. However, currently machine learning and deep learning, they are like they are the trending research topics. Both of them, they are very similar in terms of their software, and the goal is trying to make the machine can perform the human intelligent task. The difference between them is that machining, they it is a collection of statistical algorithms, which does mean that they based on statistics heavily, and most of the times they try to recognize the patterns within social data, such as Excel table. Um, yeah, so the new stuff will be will be later because I believe with some people here they may or may not attend. They don't have time to attend this workshop. So I just like quickly preview go over the slide. Okay, and for deep learning, they try to mimic the human brains, and they work with the like unstructured data such as images. So here you have the the image of the animal, and the deep learning model you can create, it can try to analyze and classify if the animal is a dog or a cat. So for Saturday, yesterday, we went over the linear regressions, and for today, we will go over the logistic regression that used to classify the iris flower type. Um, Yep. And also we will go over the underfitting and overfitting, and also some feature engineering methods. Okay, let's I move to the code. Oh, where's it? We're here. Okay. Sorry. Okay, so does anyone um, have access to the Track IT and notebook? You can just type yes or no. Okay, perfect. Yeah. Um, for those for Track IT, let's click on the trackit.acmt.co. And for the ID of the workshop, it is logistic regressions. So the first letter of each word is capital. All right, let's start. Okay. So in machine learning, classification is a problem that we try to, I would say, classifies or identify which category or type the sample belongs to. For example, um, in the email, we try to, so for every, right now in the mail app, right, there will be like a simple machine algorithm that you try to decide if the incoming email is spam or not spam. And what happened next is that if it's a spam email, then it's likely to move the spam emails to the junk box. And one of the very simple solution for the classification problem is using logistic regression. Logistic regression, um, theoretically, it is binary classifier. However, we can expand it in order to uh, use for like multi-class classifications. Here, I mean, binary classifier does mean that this model can be used to classify a dog or a cat. When I say when some people say that multi-class classification doesn't mean that they can be classifying a cat, a dog, or a bird, and so on. So more classes. So logistic regression is quite similar to linear regression that you studied yesterday. That they both examine the linear relationship between features and labels. And then the difference between the only difference is that in logistic regression they use sigma function. So the sigma function is the formula of this is the formula of sigma function. We got 1/1 plus e to the negative x. So the x here, it is the output of linear formula. What this means that the logistic regression will take whatever the output of the linear regression and put into a sigma function to convert all of the real values into probability from 0 to 1. Because in classification, the output is always probability. And based on the probability, then we can set up like if else condition to say that set up a threshold so that if the probability is over 70%, then that class belongs to, I mean, that sample belongs to that class. Otherwise, that sample belongs to another class. So here, let's say zero 0.9 is the probability output of logistic regressions. It means that 90% of the email is is a spam email. Yeah. So most of the time when you work with like machining project, um, you usually see number 0.9 rather than 90 because well, I mean, I would say just simply that because engineers they don't want to multiply to 100, so they just like simply put 0.9 there. So once you finish, you can click mark completed here and click next at the very bottom right corner. Okay, cool. Yeah, sure. So this sigma function, right? We got 1 over 1 plus e to negative x. So this x here is the output of the linear regression. Um, I will go over what is x there later on after I introduce, like after we go over the pandas, some performing some analyzing data and training on our logistic regression model. Yeah, and after those 3 steps, I will um, walk you guys through the steps to train the logistic regression model and explaining what is X here as well. So just keep calm. Yeah. Okay, right. So can't we just use the X itself, since we already know that the word value of X will give 0.8. Um, hmm, that's a good question. For right, that's correct. Yeah, I mean for the sigma function here, the X here, it could be a number, but the main goal of sigma function is that it will convert a number from negative infinity to infinity. So a number will be converted to probability between 0 and 1. That's the goal of sigma function. Does it answer your question, Eric? Okay, cool. Let's move on. So in order to explain the classification problem and loss regression, so today I will use the iris flower dataset. So this flower dataset is very common in like beginning machine learning class. You're gonna see this dataset in the intro to machine learning course at UTD. I'm not sure about the other institutes, but at UTD we use this one. So iris flower dataset, this dataset is a set of 150 samples, I mean flowers, and within 150 flowers, there are 3 types of flowers. The first one is, I mean, let's say there's a type 1, type 2, and type 3 here. I'm not really good with like scientific name for flowers. So let's say type 1, type 2, and type 3. Yeah, and so those 3 types are labels of this data set. And the features are the width and the length of the sepal and the petal. Um, so again, I'm not very familiar with like scientific terms like petal, sepal, but let's just think of they are like abstract features. Yep. So the goal of today is that we're trying to identify which species of iris the flower observation falls under. Okay. So, all right. So the very first step is that we're gonna load the first step is that we need to import dependencies. That's very important because the iris flower dataset, that dataset is already included within scikit-learn, the sklearn package here. So we're gonna load the dataset from scikit-learn. So you need to import dependencies first. The next step is that we will load the iris data. Okay. So so here I load all data into iris variable, and then as and here I separately store the features into data variable and the target of the iris dataset into labels variable. Yeah. And then the next step is that here we using data parser to create a data frame object. So here when I create the data frame object, I just given here four features only, the length width of 7 pattern. And then here I add a new column, which name Subests ID, get the labels. So what happened next is that when I inspect the first 5 rows, here the length of the width of the flowers, they are in terms of, let's say, millimeters, and the species ID, they are encoded as integers 0, 1, 2. Yep. So in classification programs, the target most of the time they will be labeled as integers. The reason is because the machine, they prefer to work with numbers rather than the strings. Okay. The next thing we're gonna do is that we need to look at the statistics of the iris dataset. As you can see here that so here let's look at the sepal length, where we have the mean is 4.3 millimeter, and the maximum length is 7.9 millimeters. The reason why we need to look at the statistics is that we need to I would say just we try to I would say like we would try to spot out some like weird numbers. For example, the length here, it should be always positive. However, if the mean is negative, that's the signal to say that we need to look at our data and fix it. Okay. The next step in inspecting dataset is that we need to check in the missing values. Okay, so in just a workshop, we're using the info function to check in the missing values. Another way to do check missing values is using this is none function and any function. So if we change these two functions together, we can also check the missing values here as well. And then just to easier to inspect the data. So, oops, what's wrong with this? Okay. Oh. Wait, guys. Just here. Okay, so probably there's some like okay, so you know what? Let's execute the label encoding section first, because so here when I execute the label encoding code snippets, what I do here is that I rename I would say that like I add a new column species name that okay, let me show you. Okay, so after I execute this code to label encoding, I have a new column species name where that every integer 0, I have a single type. Yeah, so but when you this way, I can easily see like what a file type that each sample belongs to in terms of the real name rather than just the integer code. Yeah. And go back here underneath the check iris file types, you can add a new code by clicking this button, and then you're gonna copy this code into this and execute it. So what I try to do here is that I checking the unique I try checking the unique labels or classes. So what happens is that, like, in reality, sometimes in some data sets, the labels that they give us, they are not they are not integer. They are not like numerated. It doesn't mean that they just give us the labels in terms of string, and hence um, that we should check the labels here so that we have the idea of like what type of classes of flowers within the data set. So here we just finish using pandas to inspect some fundamental information of the data set. Okay, let's move on. So after we inspecting fundamentals info of the data set, the next step is to visualize data. This step is very important in machine learning because with this step we can understand more about the data. Okay, so in the first step here that we're gonna check the balance of labels. So the balance labels here does mean that we check if our labels, the number of sample, I would say the number of labels, are they the equivalent or equal? So here for each label, the number of samples, they are all 50. This means that the labels, there's a balance of labels. The reason why I check the balance of labels because in classification, if we encounter the imbalance of labels, let's say among those 150 flowers, the number of samples that belongs to single cell flower type is only 5, then the model that we train, it is likely to incorrectly classify a sample to single cell because the number of samples of single cell is too low or too small, and then the model doesn't understand or like doesn't learn anything about the single cell type. So here we have the higher chance of incorrectly classifying the flower type here. So that's why I need to check the balance labels. So here, we have all labels. They are balanced in terms of numbers. That's perfect. However, in reality, that doesn't exist. So in reality, when you work with like real life machine projects, you have to check the balance labels all the time. Yeah. So you can click here. Click to the arrow to have the cell collapse. Okay, so after we inspect the balance labels, the next step is that we will go, um, we will visualize the distribution of the the flower samples based on the width of the petal and a sample here. So sorry, it should be the length. I'm sorry. The name is incorrect to me. Here. Okay, sorry guys, it should be the length. Yeah, so here we inspect the distribution of the flower samples based on the length of sample and the petal. So each dot here, it represents for a flower sample, and each color here, purple, orange, or red, they represent for 3 flower types. So if you look at this plot, right, you can see that the flower samples, they are separated from each other. So here you can obviously see the clear separation between orange and the purple, and between the orange and red, they are just like not really here. Here it doesn't exist very clear separation, but let's imagine you can draw a line right here to separate the red and the orange one. And by looking at this plot, it it gives me the hints that I can use some like classification, and give me the hints that I should use classification algorithms here to classify it. I mean, specifically, it is linear the logic regressions, because logic regression, what it does is it tries to draw a line that separates samples. So here, if I can imagine that there's a straight line here, right? Then that line could separate the orange and the red. Okay. Okay. Something wrong with that track IT. We will check it later on. But let's move on with visualizing the flower the flower distribution based on the width of the sepal and petal. Just remove this one. Okay, so similar to this plot. So here, x-axis, I have the width of sepal. I have y-axis, I have the width of petal. And every dot, it is a flower sample, and every color, it is a flower type. So if you compare these two plots, you can see that between orange and purple, there exists a very clear separation between these two flowers types. However, the red and the orange one, which are these two flower types, there's no clear separation. So by observing these two plots, you can kind of estimate that when we finish training our model, there's high chance that the model it it has a hard time to classifying between vesicular flower type and Virginia flower type, because there's no clear separation between these two flower types. Yeah. So by observing these two plots, you can you can kind of estimate the result or the performance of the model. All right. Oh, Jacob, if you can hide it, right? What you can do is that you can add a new line of code here. So I don't know. So if you can unhide it, you can like click this button here to add new code, or you can refresh the entire notebook. Yes, please. All right. Let's move on. Okay, so far, do you guys have any questions about the visualization part? All right. Okay, let's move on to the next slide. Okay, so we finally go to the step where we can train our own logistic regression model. Uh-huh. Okay, very similar to linear regressions. We're gonna split the entire data set into two subsets. So our first subset will be the training set and the testing set. As I explained yesterday, the reason why we need to split our data set into two sets, because the training set will be used to train our own model, and then the testing set is used to validate the performance of our model. Yeah, if you finish with the slide 5, level 5, click mark as completed here and click next at the bottom right corner. Okay, so here within this code snippet, what I do is that I try um, to column species ID and species name. Technically here, this line of code is equivalent to like selecting features. However, instead of like specifying which columns I choose to store in the features variable, here I using the trap function to trap the columns that I don't want to put into the features variable, and that's what happened. And here, I just store the entire column of target in terms of integers into labels variable, and then I put features variable and labels variable into the function train test split. And this function will help me to split the entire data set into 80% for training set and 20% for testing set. And in order to specify the test size, I just put 0.2 here, which corresponding to 20% of a testing set. And here I'm also adding the shuffle equal true. The shuffle equal true here, it will randomly selecting the samples for my testing set, and the remaining will be used for a training set. Okay, then I initialize my Logistic Regression model. The max iteration here is 100. That means that that argument will specify the model to iterate through the entire training dataset 100 times. Yes. So in machining, the more iterations the model goes through the dataset, there's higher chance that the model can improve the accuracy. The next step is that we're going to use the fit function to train our models with the input training features and training labels. So this step is very similar to linear regression model in yesterday. Then the next step is that we will, yep. So here, track IT, it got some problem. But anyway, so the next step is that we're making predictions. So let's code along with me. So here, let's add in a new code here. I got predictions equal to logic underscore model dot predict. So here we will take input the training features. So here with the input training features, we try to predict the training predictions. And after we make predictions based on the training features, we're gonna test the accuracy of a training. Oops, that's fine. Okay, instead of predictions here, let's change that one to train predicts. Yep, that should work now. No, Mina, you're not supposed to import. Well, when yeah, when you import scikit-learn, everything is included. All right. So here I'm using confusion measures function from scikit-learn with the input trend predicts and trend labels. So what does this function do is that it will create a matrix where that is showing if I predict correctly or not. So this diagonal line here, like these three boxes in the diagonal line, they represent for the correct matches. For every other numbers that in all the boxes, it represents for like um, the incorrect predictions. So okay, so here I have the x-axis is my predicted labor and my y-axis is my true labor. And as you can see that here, and for this first box, zero that matches between 0 and 0, the first type, the model is perfectly classified, and compare this box with this box. I mean, there's no like misprediction here. I mean, sorry, misclassifications. So when you look at these four boxes, it is true with the plot that we got in the visualization, because here the purple and the orange colors here, they represent for the file types named 0 and 1. If you look at this plot, there's the clear separation between two types, right? So that clear separation, it represented within this four boxes, where that there's no misclassification here. However, between types 1 and 2, there are some misclassifications because, well, it's just because there's no clear separation between the type 1 and type 2 that you can obviously see within this plot. Yeah. So, however, that misclassification is not that very bad. It has only one or two, I mean, total 3 misclassifications, and hence it makes the total accuracy score for training classification is 97%. And to compute this number, you can easily using function accuracy score right here to compute it. Yeah. So for train features, you need to execute the code snippet underneath this section. Initialize oh, sorry, right here. Underneath the split data set section here. Okay. Any questions so far? Okay. Let's wait for someone not finishing the code. I'm gonna wait here. Yes, for Avinish. So after right here, after you initialize the model, right, in a trained model, you have to execute this code snippet. You can so in the slide here, you can copy this code here underneath making predictions right here. You copy this code snippet and paste into this cell and execute it. Okay. Okay, so here, after we, after we plot computer accuracy score and plot out the confusion metrics, that's, oh yeah, sorry, I forgot to say this. So in classification terms, most of the time we look at the confusion metrics because in this confusion metrics, we can easily see that how well like the model performs, and also we can inspect like which types the model like misclassify. Yeah, so most of the time people look at the confusion metrics in classification problem. Okay, so the next step is that here we're gonna plot a scatter plot. Oh, so, so this scatter plot shows the distribution of the flower samples based on the length of the sample and the width of the sample. However, in here, I draw a line. So this line represents for the logistic regression model. So yeah, so as you can see here, when I draw this line out, the logistic regression model, it can easily classify. I don't know the name of this flower type, but yeah, but let's say it's a wait. So you can easily see that the logistic regression model, it can easily classify one type, which is the black here, from the other ones. So you can imagine that this the black color here represents for the first flower type 0, and the rest are the types 1 and 2. And because this line here, it lies right on the type 1 and type 2 flower samples, this plot shows that the model, it performs well in classifying the type 0 from the others, but it performs bad in classifying between type 1 and type 2. Okay, and after you like making predictions, you visualize how the model performs, and at the end, let's print out the predictions. So if you execute this line of code, you can print out the, a data frame that's showing the predictions and the labels. So I would say the final output of the linear regression model, it will be the code of the flower type rather than the probability. It's not the probability because that after because that the logistic regression model, when the program developers they decide, they will select I would say, let's say they will select the type that has the highest probability, and for which type has the highest probability, then that sample belongs to that type. Yeah, sure. So to make predictions right here, you can copy this line of code here. I'm sorry, right here. Trend predicts equal large model dot predict. Oh yeah. So the 80-20. So the idea of splitting the entire data set to 80-20 does mean that. So let's say you reserve 80% of a data set for training, right? So then you have your own model, and with that trained model, you will test the model on the 20% uh, on a on a testing set. So the process of splitting data into 80-20 is help us to validate the performance of the model. Yeah, that is the reason why. And the reason behind the number 80-20 is well, that's like a preferred number for um, preferred number. You can try with a 90, a 10, like 90% for training set and 10% for training set. However, we um, however, we try to, like we try to save like we try to I would say preserve like 20%, like quite a lot of number of samples for testing set, so that like we can truly test the performance of the model. Does it help, Bob? Okay. Okay. So if everyone is good with the style of um, training the model and making predictions, let's move on to the math behind the logistic regression. So as I mentioned earlier that the logistic regression model is kind of similar to linear regression model. The similarity, it lies on this linear formula, y equal wx plus b. And again, so here to make everything simple, I just consider only in this section, I just consider only one input, x only. However, when there are more like features, more input variables, you can simply have like w1 times x1 plus w2 times x2 plus w3 times x2 plus b. So if I have the formula, then I will have three input variables. Okay, so x is the input, y is the output. So if we consider the flower data set, let's say x is the length of um, let's say the sepal. Let's say x is the just a length feature, and our w is the weight and b is the bias. And y here is just the output of the linear formula. It is, yeah, y is the output of the linear formula, and that's all. It's just an abstract value. So here, W and B, the weight and bias, are two numbers that we're trying to find. Um, and the model will try to update these two numbers over time in order to help itself to classify the model more accurately. The next step is that here, we're gonna define inputs. So here our inputs have is an array of four numbers, 0, 1, 2, 3. So each number is the length of, let's say, of a flower. I mean, a flower has zero length; it doesn't make sense at all. But um, just make the demo is easier. I choose 0, 1, 2, 3, and then we define weight and bias. Again, the weight and bias here, those two numbers, we can define any numbers. It could be initialized randomly. Um, that will be fine because, as I said, that weight and bias are two numbers. They will be updated over time, because over time, so that those numbers can help the model to accurately classify file types. Yeah. Okay. So after we define inputs and weight and bias, instead, let's substitute the weight bias inputs into this linear formula. So here we have 0.4, 1.2, 2, and 2.8. Well, kind of simple, and that's it. So here we just finished with the linear formula stack. Okay. Let me see. Okay. So if everyone is good, I'm gonna move on to the next step in training a logistic regression model. Oops. Oh, there we are. All right. So after we have the output of linear formula, right? So this prediction variable here, that will be put into this big X here. Okay. So what does mean is that we can apply the sigma function here right on top of the linear formula. So the final formula for the logistic regression is that we got a prediction which is y hat equal to 1 over right here 1 over 1 plus e to the negative x, and this x here will be replaced with the w times x minus b. Okay, so to see clearly how the model performs in this cell, let's copy and paste the cell here, and you can see that. So here, the output of the linear formula is 0.4 to 2.8, and these two numbers that will be converted to probability that ranging from 0 to 1. And as you can see that here, for every number that's more, the smaller numbers, the lower the probability that number has when after we apply the sigma function. Remember here we have because in front of this big X we have negative, so that's why I have negative in front of predictions here. Yeah, and the reason why we have negative here, that is well, that is because the output of the linear formula, they could be negative as well. So here's no, I'm sorry, not because of that, to be honest. Yeah, sorry. Negative x here is just the just by default is be there in a sigma function. Yeah. Yeah. Oops, sorry. So after we apply a sigma function on top of the linear formula, all of the real values from the linear formula, they convert to the probability. I'm sorry. Let me do it again. Yeah. Okay. So for the sigma function, do you have any question? Okay, so then that's one thing I want to tell you. So sigma function, it will convert every number to probability. However, the sigma function is only used for binary classifier. Doesn't mean that in terms of the example of spam and spam email, that spam and spam email, that is a binary classification param. So we can use sigma function in the param. However, when we have to deal with like multi-class classification param, we have to use another function. It's called softmax function. However, I'm not going to cover that softmax function late in this workshop. If you can well, at the end of the workshop, I will send out the links to the softmax function, so that you can understand more how to perform multi-class classification by using logistic regressions. So yeah, what are these properties of again? Or yeah, okay. So the probabilities here it represent like how likely the sample belongs to like this class or another one. So let's say I first spam names per email, spam identified as like 1, and then spam is 0. So the higher the probability close to 1, then the model will classify that email as spam. That is that. So here I just showed you the small function only for binary classifications. If you want to do multi-class classification, you have your submap functions. And luckily in logistic regressions, the switch between sigmoid and softmax, they will be automatic, because this logistic regression in scikit-learn, it will automatically detect the number of labels within your data set. And by that way, it can easily detect it. It will switch between sigma function and submap function for you guys. Okay. So by looking at sigma function, that is the clear difference between logistics and linear regression models. Okay. The next difference between these two algorithms is that about the cost functions. So yesterday, we look at the MSE and ME, the mixed error cost function for linear regression model. Again, MS is reserved, is preserved to use for regression param only. They can use for classification param. Technically, they can be used, but theoretically, it's wrong. So in classification, most of the time they use a cost function named cross entropy, aka log loss. It's named log loss because here its farmer has the natural log formula right here. So to briefly explain it here, the y1 is the label, and white hat here is the predictions. So you set it to the white hat to the natural log and multiply with the white one. And what happens is that because our y1 right here, right, um, it it ranges from 0 to -1, and if you put a number less than 1 into natural log, the log will return negative. And hence, to make all of the error becomes positive, so we add the negative in front of the multiplication to convert all negative errors to positive. And then the sigma symbol here with the 1 over m coefficient, they trying to compute the average of the loss. And that's what happens. So in code, so first let's default the labels. So here our labels is only 0, 1, 1, 0. As I explained earlier, that sigma function is it is used for binary classification rather than multi classes. So my labels only has 0 or 1 only. And then to compute a loss, I'm using just copy this code into the cell, and then I get the loss. So here in NumPy, we can easily use the log function. So this log function, it will compute the natural log of a number. Okay, and then we multiply the labels, and the natural log of predictions together by using that function. The dot function here, why we use it, because if you study linear algebra, dot function is it used to multiply like matrices. Okay. The dot function here is used to multiply matrices and vectors. And then here I need to multiply -1 to convert all of the errors to negative, and divided by 1. Divided by 4. The 4 here is number of class samples in this demo, and here's my loss is 0.09. So deep learning is about giving a program a lot of examples so it can infer the property of classifying something to a function. Yes. Well, machine and deep learning, they share the same mechanism, and that way. So both of them, they require a lot of data set. A lot of data, sorry. Yeah, the only difference is that for machining, I would say machining algorithms, they are heavily based on statistics. However, for deep learning, they adapt something like called neural networks. Like they just try to mimic the human brains. But beside that, everything is kind of similar to machine learning. That does help Douglas. Douglas? Sorry if I mispronounced your name. And also that, like as Douglas mentioned about deep learning, so technically in deep learning, this loss function already used in deep learning for classification program as well. Yeah. So after we making predictions, we apply the sigma function to convert all of the outputs of linear formula to probabilities, and then we compute the loss functions based on the cross entropy function. So we got a loss, we got a predictions. The next step is that we need to update the weights. That process is called optimization. So within the optimization, well, both machine and deep learning, they use ChexNet. So when we use ChexNet, what does it do is that for every iteration through the training data set, doesn't mean that for every iteration, the model will will go through the entire data set and then update the weight. So the process of updating the weight will be repeated until the loss computed by the cross entropy function reaches the global minimum. To simplify the process in terms, here I have a plot right here that initially the cost is very high. It is something like the cost initially very high is something we expected, but by using ChexNet, the cost over time, over iteration, the cost will be minimized and reaches the global minimum in this. And to update the weight, we just simply that we get a new weight minus we get a new weight equal to O weight minus D loss. The loss here is just the loss computed by the cross entropy function, and the D here is the derivative of the loss. In the simplest term, you can think that D loss is just the magnitude of the weight update. So the process of optimization using ChexNet is very similar to linear regression. So here I have this code here, and if I execute it, I have the new weight here. So for every machine learning and deep learning algorithm, most of them they have they need first step is they need to make predictions, and then they compute the loss, and then they optimize itself using creating extent. Okay. So do you have any questions about so far about like the intuition behind the logistic regression? Okay, looks good. Okay, so okay, let's move on to some validate step. Oops. Okay. All right. So let's making some test predictions. So here, when I'm making test predictions, I use the logic model that I pre-trained earlier, and then I use pre-function with the input test features. And okay, so this line test predict probabilities here, they technically they just retrieve some I would say some parameters within the model, but that doesn't matter a lot because those numbers that will be used to plot the confusion matrix. So again, here I have my confusion matrix for testing for test predictions, and if you look at uh, the four cells in the top left corner of the confusion matrix, you can see that here um, the model can easily separate between type 0 and 1, and there's no misclassification here as well. You see that? And this one tells us that the model still, in the validation step, the model still can perform. I mean, it still can classify the type 1, the type 0, and the other classes well. However, here we observe the misclassification between type 1 and type 2. And this is true. It is true. This is true that it is true that the model is still get a hard time to classify type 1 and type 2. So if we observing this confusion matrix, it is true when we observing the plot in the visualization process. And here I also have an accuracy score about 96%, which is slightly smaller than the 97% our training predictions. Yeah. So what happens here is that you can easily, because the difference between the difference in accuracy between training and test predictions is only 0.01 percent. That based on that, we could say, yeah, the model performs quite well. However, it's not, because I mean, obviously it's not, but like I can guarantee that the model can work perfectly in reality. Like you put this model into predictions outside there, it may not work well because the number of samples we have is only 100, 150, and with that limited samples, the model may easily get overfitting. So overfitting is the situation when the model performs bad while in training, but it performs bad in testing. That is what that's the definition of overfitting. So here, the reason is because of the limited data set, or the model is too well, it's too complex. So what you can do is that you can simplify the models, or you try to collect more data for the model. And opposite to outfitting, you have underfitting as well. So unfitting is a situation when the model performs bad in training, but it performs great in testing. The reason, so ver- very similar to yesterday, that underfitting happens when the model is just too simple and or less data features. So to pretty much that, to prevent underfitting, what we can do is we need to try and implement more complex algorithms, models, um, and then beside that, we can add more features. What I mean add more features does mean that, let's say here I have four features for the flower type, like length and width of sepal and petal. Then you can add more features. I mean, you can try um, to look for more uh, look for more features, such as like let's say location of the flower. Yeah, because let's say this is such a like the location where the flower is planted, and that's one. Maybe that new feature location may help the model to to perform well and prevents underfitting. And that, so to clearly understand the what is underfitting or overfitting, I have a plot here where that the black light here, it represents for the model, and the dots here represent for the data points. So underfitting happens when the line here, it doesn't align and follow the no the fluctuation of the data points. Yes, this is underfitting. For overfitting, um, the line here, you see that the line just, it lines right on top of the data points. It's just too fit to the data points. The perfect and the like the best situation that all of engineering expert in machine they want and they pursue is the model, the line here, just right fit to the data points. No, there's no like off from the data points or just too fit to data points, just right fit. And that is the end of the workshop. If you want to look at more, if you want to like explore more about logistic regression, you can click on this link, or you want to explore more about small function, you can follow this link just to study more. Yes, and the recordings and all of the notebooks for this logistic regression workshop will be sent out shortly. So, do you have any question? Oh, you're welcome.